Okay, so now we have Fourier coefficients for each of the 4 state space matrices. We can apply frequency lifting to obtain a frequency lifted time invariant representation of the state space system represented by these 4 non-lifted matrices. In other words, going back to the main, we see that we can do now frequency lifting. I will do frequency lifting with a maximum harmonic rank of 3. And then technically I could also modify the forced harmonic rank. For now I will just keep it to the value given by Hm, which was equal to 6. To be sure you do not lose any information, you technically have to use a truncation rank equal to 6, but just to make the calculations very, very fast, in the description of this toolbox, I will keep it to 3. You see, it's very easy. In any case, you could put it to any value, any positive value, and it would work. So I would like to obtain the harmonic state space model of my single phase, of my linearized single phase MMC. I do F9, and it tells me that DSA get harmonic state space. The harmonic state space model is defined as DSA LTI harmonic state space system. This is a state space model with 14 outputs, 14 inputs, and 63 states. So why 14 outputs, 14 inputs, and 63 states? Well, because we have 2 inputs with 7 Fourier coefficients. Why 7 Fourier coefficients? Well, because we truncate at maximum harmonic rank 3. So we have 3 for the negative frequencies, 3 for the positive frequencies, and 1 for the constant Fourier coefficient. That is indeed 7. We have that for 2 outputs. We have also 2 inputs, and we have 9 states. Each of the 9 states have 7 Fourier coefficients, so that is indeed 63 states. Also, the toolbox tells us that the system does not have internal pure delays, so this is indeed a harmonic state space and not a delay harmonic state space. Alright, this essentially means that we can calculate eigenvalues quite easily. I will get the calculation of frequency responses right after. This is not a delayed system, so I can comment these lines related to delay differential equations and just run this DSA X, which will run itself the eigenvalue calculation of, the famous round A minus round N characteristics of harmonic state space systems. I run this one and I get the eigenvalues of the harmonic state space representation of the single phase MMC. So as usual, it takes a little bit of training and experience to interpret these eigenvalues. Mostly we will be looking for the centermost eigenvalue of every set. So this one, it is centered at 0, so I know that this is the centermost eigenvalue of this particular eigenset. This one, 1, 2, 3, 4, 5, 6, 7. I assume that there will be a shift of +1. So 1, 2, 3, 4. This one will be the centermost eigenvalue. There are 2 of them, so sometimes it's a little bit tricky, but by means of participation factors, we will be able to determine exactly which one is related to the eigenset that is centered around 50 Hz. Let me be specific and run a participation factor calculation. The participation factor calculation requires a new structure that is PFA, participation factor analysis. It requires a set of eigenvalues, a set of right eigenvectors, a set of left eigenvectors, as well as names of the variables that you are working with, and we will see the rest afterwards. So just making sure that once I have done frequency lifting, I have the harmonic state space model stored as mentioned by Matlab in there. So just checking this, I have indeed the matrices related to the harmonic state space. I have the A minus n. The minus n is already included in there. I have the tuplets, block tuplets B, block tuplets C, and block tuplets D matrices. So the reason why I do not provide n as a separate matrix is that it is already included in this particular state matrix A. So A accounts for round block tuplets matrix A minus round matrix n. I have also the system as a Matlab system, the eigenvalues, the right eigenvectors, and the left eigenvectors. So those are the elements that I provide, that I give to the participation factor structure. Now I can run all of this, F9, and I obtain results. I see that I have a big table with many participation factors, and I have also a list. Okay, let's have a look at that. I have modes that have indices, and they are identified in terms of their real part and their frequency. So naturally, the frequency is just the imaginary part divided by 2 pi, and the damping is calculated as well. And then we have the participation factor analysis based on the magnitude of elements. You can find the exact formula in the first chapter of my thesis or in the code. And then you have this table. This is the table of participation factors. It tells that mode 1, there are multiple states that participate in mode 1. There are modes, there is state 63, 62, and 56. These states are these variables, and naturally we are working with a frequency lifted system, so these are identified as being the +3 channel, or at least, or in other words, the +3 index Fourier coefficient of this particular state. The correlation is, let's say, the weight of this state into this mode. Each state has a particular correlation, so a particular weight in the mode, and then I display the cumulative correlations up to something close but not equal to 100%. Otherwise, some lines of the table would be very long. This is something that you can change minorly in the code. Let's take just an example. This mode number 15, there are multiple states that participate in it, and I see that the main state that participates in mode 15 is the second harmonic, or the second Fourier coefficient of the alternating current for 82%. Now, if I look at this plot, I see that all the modes have a value. Let's say if we are interested in this mode, mode 12, well, naturally, we know where to find it. Here's the one. Let's say we are interested in mode, another one closer to the imaginary axis. These two modes, 52 and 50, I could scroll and eventually find it, but I can also just say that I would like to check modes 50 and 52, and I get directly the lines in which I am interested. And I see that these modes, they are related to the alternating current controller as well, so up to a cumulative participation of 87.4%, and next to the circulating current controller up to, well, with a 90 8.4% cumulated. In some cases, this plot becomes very, very difficult to read because you have many numbers. Let's say that you are not interested in numbering these modes. Well, you can display only those that are interesting to you. Let's say everything with a real part larger than -7 and with an imaginary part that is positive. Something you can do here. Imaginary part should be positive, and everything with a real part larger than -7. Naturally, I have to make this empty for it to work. Okay, so here is the result that is visually easier to check. Now I have only displayed the numbers for the modes with a positive imaginary part and a real part that is larger than -7. So I can see only the numbers of these modes. And now I can say, okay, mode 29. I could scroll to find it, but I can also ask for its mine. 29, and there it is. All right, I think you get now how it works with the participation factors. Earlier, we were interested in knowing which one was the centermost of this eigenset. I know it is centered around 50. It's either the 61 or the 63. 61 or 63. We see that this one corresponds to a centermost eigenvalue, or to the center of one eigenset. So the 61 is actually the one. With some experience with frequency lifted systems, this is something that you will be able to check by yourself.